My First Contexts. An Introduction to Functors, Applicatives, and Monads. A loving banter to a loving community, where despite all my chanter, some still refuse to teach type theory at university. Cold outside on the starry night, a value was frosty, so it wrapped in a kite. A magic kite, though indeed it would be, vanishing the value occasionally. Maybe, in general, this type is called either holding a value or nothing at all. As null pointers ain't no good idea, it is said, modern languages are now using the maybe type instead. The problem, however, with this extra wrapping, normal functions can no longer function to get in. Flipping a boolean that's wrapped in a maybe is harder to do, lacking additional places. Therefore, we define what it means for a function be applied to a value in a maybe construction. Applying a function to a maybe has cases. One is for nothing, just for the element in stasis. Applying to nothing, nothing sure has been rooted. Applying to just f of the value computed. Going back to our Boolean example again, solve it with a simpler function we can. Another example of this is a list. A list wraps a type in a context its elements are multiplied. So a list is either something empty indeed, or an element attached to the rest that we need. Applying a function to this is now easy. Nothing happens in the empty case. In the const case, we apply the function and continue so sleazy, all values transformed we now face. Such structures, in general, we call functors. A functor here is a transformation between types, where the functor map function at least suffices the property that applying ID stays ID and functions are preserved under composite. Every time we have a type in Cabal, what we are wrapping around it, the context we call. Next up, we do something funky as that. Not just the type, but a function we wrap. A function that is wrapped in a context can sure be applied to a value in the same type of law. In a maybe we check whether both values exist. Any other case, sure, is a value we miss. For a list, the concept is not just as easy. Here a list of function does not always match its meaties. Therefore, for every function there is, the values for all applications will fizz. This can be used, as is often taught, to model search problems and other good thoughts. For now, we just build all possible combinations, but later we apply to those combinations filtrations. This way, only our wanted solutions are left, so let's first build a concrete implementation of that. We first map each function over the list of all values. The resulting lists are then concatenated for mind truth. So applying a list of functions to a list of their arguments gives all combinations of functions to garments. Additionally, both list and maybe have functions that lift any values to thee. Pure it is called, and together with apply, an applicative functor we are getting for thy. With the operators we do something funny. Imagine the context to be just ID. The definitions for fmap, pure and apply now ain't cunning. Pure is ID and functions are applied, so they're running. Therefore, every function application, like fabc we can see, could be written with our new operators, like f applied to a, b, and c. With the new operators, however, we can clearly change any context at hand. With context ID, this is plain function application, but with maybe already, each value might be rationed. With lists, this is even a greater complication because we get all combinations of argument applications. Oh, I wish our languages would lift every function application in a context to see. Never more need for this context overheady, sure some sort of solution there'd be. We call part of this solution the idiom bracket. It lifts our functions to a nice little packet, so fabc that we write to this cell desugars to f applied to a, b, and c pretty well. Next up, we look at contexts that are even more intriguing. They make up the functions with the state they are being in. Sure, that is not just the soul of their queue, but it shuts up the people claiming state in functions? Sure no couldn't do. Imagine a context represents a piece of a program. Its wrapped value, the result that it gives, where there would be a way for the result of the first codon to be piped to the second that lives. There are two different ways to express this. The first is an action that results in a program transformed into an action returning what's in it. This action now inevitably means the result of its intern can be unwrapped indeed. This operation is called a join, but more famous sure, the other side of its coin. This unwrapping sure is a cumbersome look. Better it'd be if the first action we took would pipe its result to the function that then returns the next context to be continued again. This operation is called a bind, and in its simplicity it's one of a kind. Together with a pure that we call return, a few laws to make sure that we earned correctness, and then a monad we defined. Its generality stunning, computation now inlined. Given a functor, the bind can be expressed via join, or in general join via bind, one of the two now sufficient to leave confusion behind. And this is irrelevant for those who haven't heard it, but the join operation is the bit where the sentence "a monad is a monoid in the category of endofunctors" makes sense. So, we go and speak of categories through this lens. Anyway, so programs with return values we can now express to a point where the pure is now called return nonetheless. To build an example, useful and quite hard to hate, the monad for carrying a state we create. Every time we're dealing with state, a state transition function we always create. In this case, not only the transition we define, but also the result of the computation we gain. If you want to return the state in question, you can put it into the resulting section. Setting the state, why the hell would you not? The new state you put, the old one you drop. But oh mighty universe, how annoying it were if passing by hand the state we need care. The monadic bind allows this to be fairly looser by hiding the state passing away from the user. In the monadic bind, the first argument is a state transition function, the second argument a function taking the first of the conjunction to transform it into a new state transition, transforming to a new state transition emission. We want this to be a function taking a state that sure we could put into the first operation and make the tuple containing the next state and more the result of the computation that we have done before. Then we take said result and easily we plug it into the consecutive function. With luck, it now returns our final result, the tuple of output and state in a pub. The other functions that we just described can also be defined for the state monad, right? It will, however, be, for the time to be freer, left as an exercise to the enthusiastic reader. Important is just to wrap up the latter that state transition now looks significantly better. Assume now we want to write a good old if-then-else. But assume that the condition needs the context, so it tells the content of a variable to be either true or false, and chooses the branch for subsequent calls. First, we run the condition and then pipe the result to a function that can, depending on whether it returned false or true, return a different computation next up to do. If you do not like the anonymous function, extra syntax can be used as a junction. We call it the do notation, and all that it does is put the binds between operations autonomous. Particularly handy this does come if the binding functions are needed for more than just one. It also looks just cunningly close to imperative programs other languages chose. Sadly, a further simplification is course via idiom brackets does not directly work because they desugar to something where all operations are run regardless of whether we need them to be done. This will mean here that the state might be weeded even for all the results that ain't needed. If like in maybe unnecessary actions discount, all useful of the actions are still put to the ground. If necessary though, do notation is no crime. Functional it does stay anyway all the time. However, with the right use of join and idioms we can often avoid looking imperative again. Not like the look needed changing to the latter. The fact we can exchange our context already makes us better. Don't believe me? Go ahead and change the context to list. Your code now for search problems in programming is. Just remember, if all of this is a bit much at first, rewind the video for your understand wanting thirst. Also, play around with the concepts at hand. All the contexts you get will be yours to command. Let us recap all the things we just saw. We first started off using functions raw. Now, because context is important, we said we wrapped all the values in a context instead. To do this, we needed two main operations. Pure/return to lift into context causations. Context-wrapped functions and arguments are then combined with an operator to apply them again. Idiom brackets we were using then to force context operators to vanish again. If now our function spits new context so formal, join we could use to continue as normal. If instead you are going for an imperative look, bind you define, so the do notation took it upon itself to bind everything all together, and you can intermediate values wherever. This might be the hardest to understand all the way through, but once understood, there is no stopping you. For any time your context should do any more contemplation, no touching your old code. Just redefine your operations. And whenever someone asks you, what is the best imperative language? The answer is none. The best imperative language is a functional one. Whether state, exceptions, search, or fun, typed functional programs can sure get it done. Merry holidays again to all that teach logics to their kids, kin, and enthusiastic students. For more material, please see the video description. This was Arvid Friedemann's My First Contexts. Happy logicsing, my beloved intelligences.